can tell we're already prepped with questions. So I was just going to ask him whether he threw up on the Vomit Comet. We're super excited today to have Krzysztof Skonieczny with us, or back with us after 10 years since his PhD. And I found out it's been like 10 years since he was last here. So Chris is at, he did his PhD work here. He was an undergraduate at University of Toronto, but now he's at Concordia University in beautiful Montreal, where they have excellent eclipse viewing, I understand. But as was suggested there, Chris has done some really exciting work in mobility, including some very exciting testing that we would love to do, but certainly love to learn from. So without any more, Chris, take it away.
Thanks so much, David. Thanks very much. So today I'm here to talk to you about the extension of everything I started learning here at CMU, where it was really instilled in me to get out into the field, get out into the relevant environments in order to test the robotics that you're doing. And so today I'll be talking to you about two of those scenarios. One in field tests out specifically near Montreal, and then in the relevant environment of reduced gravity. So as far as an outline for today, for the reduced gravity part, I'll be going over some of the existing mobility testing methods, our experimental methodology and results and recommendations. And then on the field testing side, we'll talk about skid steer power consumption and looking at how to arrange for energy optimal path planning for skid steer rovers based on that power consumption. So the motivation for the reduced gravity aspect of things is from some of the difficulties translating mobility on planet here on Earth to off planet and on Mars and the Moon. So on the Moon, they had some issues during Apollo 17 where the LRV spun out in place, had the astronauts come pick it up, move it out of the way into a fresh regolith and continue on their way. On Mars, Spirit wasn't as lucky. Of course, there were several contributing factors, but the ultimate problem that Spirit ran into was sinking into loose regolith. And then the interesting thing from the perspective of this research was that they actually set up a very high fidelity representation of the configuration that Spirit was in at JPL with a sand tilt bed at the right angle. And they were actually able to come up with mobility commands that freed the Spirit SSTB Lite, the Spirit model, in the lab. But when they uploaded those commands to Spirit, they didn't end up producing the same results. So that was one of the reasons that got me thinking about this difference between operating in Earth gravity and reduced gravity. And as Red just mentioned before we started, this idea that you have the right weight of the rover doesn't translate necessarily into having the right weight in the soil itself and the gravity effects on the soil particles. So there are a number of different approaches that people use on Earth to try to mimic the mobility on these reduced gravity environments. And one of these is this reduced weight testing. So you can have that with gravity offload or with, especially in Mars, it's a little easier. You can actually just have a reduced mass model of your rover. This is Scarecrow, which is the 3/8 mass Mars weight version of the Curiosity rover. And this here is the gravity offload test off of Scarab, doing some digging. This is actually back from my PhD days, and it's fun to throw in there for that reason. And summarize many years of grueling work in one figure on one slide. Other methodologies that are used include trying to match soil response. So that means looking at data from Apollo, for example, in the lunar context, where astronauts put cone penetrometers into the soil, got a certain response, and then try to generate simulants here on Earth that produce the same sort of response. So ignoring the difference in gravity and just hoping that those two responses being equivalent give you an equivalent mobility response. So this was the idea behind the GRC-1 lunar simulant developed at NASA Glenn. And so we'll be looking at that as a potential methodology as well. And so here's the astronaut putting that cone penetrometer into the soil, into the lunar regolith. Finally, we can also apply what are called granular scaling laws. So this is something that's equivalent to like in the field of aeronautics, using things like Reynolds number and the similitude to in a granular material context. And using that to account for differences between your test and reality, whether that's the scale of the robot that you're testing, or, as we'll see, the gravity level under which you're testing. This isn't an exhaustive list. You could also do things like test with particles that are reduced density as well. There are other ideas out there, but these are three of the big ones that often get utilized. And so we've looked at actually testing out these various theories in the relevant environment itself, in reduced gravity. So to do that, we developed this test rig where we can do single wheel mobility testing, and we can also do automated soil preparation so that we can run tests in parabolic flights. And for 20 seconds, we get to experience lunar or Martian gravity, and we can see what kind of effect that has on our mobility. So here's a quick video of our soil preparation. So this is fully automated to be able to run within the constraints of the reduced gravity flight. So we close up our test bin, we blow air through the soil to loosen it. Then we have a vibratory compactor that brings the soil to the specific density and preparation that we want. And then it's ready within, about 20 seconds. We're ready to run our wheel-soil interaction test. You can note there's a little camera that's following the wheel along. That's looking down into an angled mirror that is then looking through this same glass interface that we see here. So we're able to collect force data, sinkage data, as well as actual soil motion data from the tests.
Just to clarify.
Yes.
Every motion we just saw, from aerating the soil through the end of the run, is less than 25 seconds.
So it depends on the settings for the particular soil and the preparation that we're doing. But yes, for this, what I was showing here, we had some cases where we needed to vibrate more, so we were going up to 35 seconds. But yeah, in around 30 seconds. And we would just hit the one button, and we would set up our parameters ahead of time. And then once we were at 1G level flight, we would hit our soil prep and about 30 seconds. Yep.
So the 35 seconds would be during the flight in lunar gravity, right?
No, so we do the soil preparation itself in 1G. We do that in 1G in flight, and we actually have in another flight during the same campaign, we do some cone penetrometer characterization, so we can then reproduce that same soil preparation in the lab for direct comparison. And so here's a video showing one parabola. Once we've already prepared the soil here, you see some of the instruments. You see the gravity level that we're experiencing. So we're in the bottom, we're hitting up to 2 Gs right now. We're in the bottom of this curving up. You see the angle, pitch angle of the aircraft rising up. Our speed reaching up to 400 knots, getting up to 50 degrees. And then we're going to go over the top. Our gravity gets down to 1.6 G. Students having lots of fun. We're going over the top. You see the profile there and the angle. So now we're pointed down 40 degrees down towards the ground. And then we're going to go back into the hyper-G from that. And so we've done multiple campaigns with this, including in October of 2020, which, if you remember, was a fun time for everyone, where there was, on that particular campaign, there was an extra rule, which was no vomit on the vomit comet allowed for COVID considerations. So I made it through that one, just barely, but it's been lots of fun getting to fly this multiple times. So looking at the actual results, from the multiple campaigns, we've been looking at these different kinds of methodologies that I presented that get used. And here we have the methodology where we're applying equal weight on the wheel, but the testing is done in 1G, thus the soil is under the influence of 1G, or the soil is under the influence of Lunar-g, and we also actually did Martian G as well. And here on the plot on the top left, we see the drawbar pull, so the net traction that the wheel is experiencing. In 1G with the blue circles, and in 1.6G, Lunar-g, with the green triangles. And so despite some noise in the data, we get a pretty consistent drop on average of 20% in terms of traction in the Lunar-g relative to our 1G tests. Similarly, but conversely for sinkage, we're seeing much more sinkage in the Lunar-g than in the 1G with the equal weight applied in those two cases. Then looking at the soil motion through the sidewall, again, the same experimental conditions in all three cases except for the gravity influence on the soil. We can see the amount of difference in soil mobilization below the wheel in 1G in the left column, Martian G with more motion in the middle column, and Lunar-g in the right-hand column, where the blue, dark blue is representing static soil up through the warmer colors, red representing sort of the maximum soil velocity, soil motion. And we observe a dramatic increase in the amount of soil under the wheel that's being mobilized in this reduced G versus higher gravities. So this was the different segments there, the rise, plateau, and so on. This had to do with, this first experiment was with a compliant wheel. This was for the ESA ExoMars mission, the engineering model wheel for that rover. So the compliance in the wheel meant that the data had these transients within each cycle of rotation. And so we just, for one-to-one comparison, we split up the data into these separate segments.
That answered my question. Just to confirm, that's why we're not seeing any grousers or any localized effect from grousers.
So there are some small grousers, but they're not big enough to sort of show up in this masked display. They're small grousers because it is a compliant wheel, so they're not looking for as big of a grouser profile.
Or here's some news about wheels with grousers.
Not in this particular talk. So I've got some stuff I could happily share on that, but not today. So another thing we did was trying to characterize this assumption that goes into using GRC1, namely if we get a certain cone penetrometer data in reduced gravity, what happens if we operate at that same cone penetrometer reading in Earth gravity. And so we did flights where we had a cone penetrometer on our rig, as shown in the bottom right here. And then we took data flying at 1G level flight, so we're under 1 gravity, but still in the airplane, to sort of take into account any differences between operating in the aircraft versus in the lab. And then during the parabola, we would take cone penetrometer readings again. And that's what we see with the red squares. So we would see a significant reduction in the resistance that the cone penetrometer sees. And then in the lab, we would then do a much looser soil preparation in 1G so that we would get these green triangles on the far left there, which are at essentially the same amount of cone penetrometer resistance as the red ones there. Maybe I should get a laser pointer. But so the idea here was to figure out what cone penetrometer values we would experience in reduced gravity, and then try to replicate that same cone penetrometer resistance in the lab. So this is what we saw in the flight, in the parabola, and then we would set it up in 1G, but at the equal cone penetrometer resistance in the lab. Then on the same data set, we could also check these granular scaling laws. The granular scaling laws actually assume that you're operating at the same density. That's one of the assumptions. So that's why we also did these these cone penetrometer insertions in level 1G flight, so that we could then in the lab also replicate that condition and know that we have the same soil preparation in the lab as we had in the aircraft. And then those granular scaling laws allowed us to test with a small wheel in the lab versus a large wheel in the aircraft.
Chris, the question is for the parabolic flight, right? You're not obviously perpendicular to the vector, the gravity vector, right? Did you account for that the fact that you're getting to parabolic and you're just seeing a component? That's one question. Then the second is, what happens with the kind of the compression of the soil? Like, is there an effect from the parabolic on how the particles of the soil move in order to have good confidence on the results, on the cone penetrometer results?
Right. So on the first question, we have the IMU data from the aircraft. And despite the fact that we're at these angles, because of the trajectory of the aircraft, the net acceleration vector is still perpendicular to the base of the structure. So we didn't actually have to do any correction for that. And then the second question, sorry, remind me again. The effect on the soil, right. So we looked into that, not directly, but we ran some tests where we did cone penetration before a parabola, and then we had some where we did the soil preparation, we did the parabola, we didn't do anything during the parabola. We just let the soil react to the experimental condition, and then after we returned back, then took the measurement again. And we didn't see any difference between the things. And also visually, from just monitoring it, there wasn't any obvious amount of compression or dilation or expansion of the soil. So of course, there is something happening in the soil as it experiences these different levels of gravity. But it wasn't enough to change the outcome of our cone penetrometer tests pre or post parabola.
The test had in mind width and depth, I guess, of the soil. So this kind of side wall effects, etc., were.
Yeah. So for the cone penetrometer, for sure, we set it up specifically to have significant depth because we knew that was important. For the wheels, we are up against the glass wall. So, of course, there is that edge effect, but that's what we see in all of our tests in the lab as well. So this is the setup for granular scaling laws. I won't belabor the point on here, but these are the terms that are the dimensionless terms that come out of the analysis and are the ones that need to be kept constant between your two test conditions. And so you have a certain number of degrees of freedom to set up your experiment, but then once you've selected two different gravity levels, for example, and two different masses and lengths, then everything else is dictated by keeping these values equal between your two tests. So you have a few options for how to do your granular scaling laws setup. And I have a little bit of info on that coming up. But the main thing is keeping each of these values consistent between your two setups and your two gravities. And so as far as results are concerned, here we have our drawbar pull or traction values and our sinkage results as well at a few different slip conditions, with blue data representing the data collected in reduced gravity, green data being our granular scaling laws, predictions from the tests that we ran in the lab in 1G with, according to the granular scaling laws, and red being the GRC1 at equivalent cone penetrometer readings. And we see as slip increases, the difference between the Lunar-g and the GRC1 predictions starts increasing. And perhaps most dramatically in sinkage, the predicted sinkage in GRC1 is lower than what we see in reduced gravity and in our GSL testing as well. And our GSL testing was tracking the reduced gravity results very closely up in this low to sort of moderate sinkage regime, slip regime. At higher slip, it gets harder and harder, no matter what technique you use. But still, GSL was coming closer to the reduced gravity data than the other approaches were, especially in terms of sinkage. So this is so the main takeaway from this was that these granular scaling laws did seem the most promising for implementing tests on Earth relative to reduced gravity. And so we looked into that more and looked at what are some of the practical things to consider. There are some other versions of granular scaling laws that take cohesion into account. We did some tests to show that cohesion in lunar Regulus simulants is low enough that we don't have to take it into account, which gives us enough degrees of freedom in our GSL setup that if we wanted to, we can select to have the same size wheel in our Earth tests as our lunar tests, which is convenient. We can also, with using one of our other degrees of freedom, allow the Earth mass of our system to equal the mass that we're sending into the lunar condition, being clear that this is mass, not weight. So, 50 kilograms and 50 kilograms or what have you. And with those two things specified, you end up that because your gravity condition, of course, has to be different, that's the whole point of the test, that uses up your 3 degrees of freedom from the approach. And so everything else is determined based on that. And what that determination results in is that your velocity on Earth and your angular velocity for your test needs to be, works out to square root of 6 for the factor of 6 difference in gravity. Essentially, you need to operate at a higher inertia to keep the ratio of inertial to gravitational effects equivalent. So whereas in the lunar environment, the reduced gravity tends to manifest as sort of easier mobilization of soil and sort of more dynamic effects, like if you watch some of the videos of the Lunar Rover LRVs, the soil motion is very dynamic. To get something equivalent in Earth gravity, you need to operate 2.5 times as fast. Now, that's if you're operating with vehicles that are driving as fast as the Lunar Rover vehicle. One additional gift is that one of these factors, one of these non-dimensional quantities in the granular scaling laws is this here, velocity over square root of characteristic length times gravity, which is the Froude number. Now, the Froude number is exactly this ratio of inertial to gravitational effects. And one thing that's nice is that if you are low enough with your Froude number, essentially that's one of the criteria that often gets used for ignoring inertial effects. So there's been data in the literature showing at sort of low speeds, so 1 to 5.5 centimeters per second, for example, the effect of the speed on drawbar pull, for example, versus slip is small to negligible. So if you're operating at a low enough Froude number, at low enough speeds, you can actually get away with ignoring the effects of velocity, which means you can work with the same size rover, you can work with the same mass rover, and you can operate even at the same velocity as you expect to, which is much more convenient than having to go up into a parabolic flight or build a gravity offload machine or any number of other approaches that you might consider. So in addition to informing sort of experimental techniques and validation techniques on Earth, doing this kind of work is also very useful to use for validating more complex modeling approaches. So we've done some work in that area as well, with collaborating with various people in and around Montreal, for example. So the next part of my talk, I wanted to move on to talking about skid steer lunar rovers. I chose a couple images to be familiar to folks here. And then these are some of the ones from the planetary analog terrain at the Canadian Space Agency, where we've done some testing as well. And on this front, there's it's really informed by some observations about how much energy, or how much power, rather, it takes to use a skid steer rover versus an explicitly steered rover at tight turning radii. Now, since the energy you use is the integral of power over time, we were interested in what happens when you do maneuvers that are combinations of turns and straight line drives. And specifically, we were comparing what we call CLC, or a circular arc, then line, then circular arc type path, to what we could call a PLP, a point turn line, point turn path. One more quick definition. We coined this term R prime to specify a turning radius, the turning radius you happen to get when you don't turn your inner wheels with a skid steer rover. So if you're just driving your outside wheels. For really tight for point turns, you're operating the same velocity in opposite directions. For really tight turns, you have your inner wheels still going backwards. And then eventually you get to a point where you're not turning your inner wheels. And then finally, for much wider turns, you're driving forward both sides, just at varying velocity, right? So this turned out to be an important turning radius, the turning radius at which the inner wheels aren't turning. And looking at data from the Canadian Mars Yard here, the planetary analog terrain at Canadian Space Agency, also some tests done out in White Sands, New Mexico. To give the final picture here, essentially, when you look at a CLC versus PLP, this is power versus time. So the integral of these two curves are your energy. Taking a wider turn not only is less power intensive in the turn itself, but actually the fact that you're making progress during the turn allows you to keep shorter linear segments between your turns, such that you're shortening your overall maneuver time, and also the integral, and thus your energy as well. And this is at the cost of just marginally more time in the turn, because of obviously you need to go more than you would if you're turning directly to where you need to go. So this was well, we looked at this from the perspective of power versus turning radius, and looking up at power models for skid steer rovers in the literature, they predict this relationship where up to R prime, which is one of the reasons it turns out to be important, the model says you have constant power use depending on your turning radius, and then your power decreases as a function of 1 over R past that point. And it turns out, and I won't go into this today, but turning at this radius, according to this model, turns out to be the optimal turning radius for these kinds of maneuvers. And we validated that with some tests on hard ground, which this model ends up being appropriate for. The model makes frictional assumptions, essentially. So driving on concrete, it's a good enough model for that. And here we have turning radius over r prime, meaning that at 1 here we have a turning radius of r prime. And so at different turning radii, either smaller or larger, here on the y-axis we see the amount of energy savings relative to PLP. So the amount of energy use relative to PLP in percentage. So this minus 10 represents a 10% energy savings relative to PLP. So turning with wider turning arcs of r prime, for example, saved us 10% energy for this CLC maneuver as opposed to the PLP. And so that worked well enough on hard ground. But then we wanted to look at how that translates to operating in loose soil. And comparing to this model in terms of the power consumption, we noticed that we saw actually, instead of it being constant power up until r prime, we would see this huge spike in power right around and below r prime. And actually between the range of half of the rover width and r prime. Now, half of the rover width might be what you would expect to turn as your turning radius if you're just turning one side and not the other in an ideal case. You'd have the one side sort of planted, just turning around a point, and then turning with the other side. But because of the lateral skid that is inherent in skid steer rovers, the actual turning radius that you achieve is always bigger than half of your rover width. So you always end up with this region existing where you have a region between half of your rover width and your r primed. And we noticed this spike in power consumption right within that region. So we wanted to see what's going on there. And essentially what happens is that because you're below r prime is where your inner wheel velocity is 0, and for tighter turns it's negative, meaning that below r prime, your inner wheels are always turning backwards. But because your actual turning radius is more than half of your wheel width, your rover width, sorry, these wheels, despite turning backwards, they're actually being dragged along a circle that has a forward component. So just the fact that you have lateral skid causing this region to exist, and you have these turning radii that are still negative, even though your overall turning radius is more than half of your width, you end up with this condition where the wheels are being dragged one way while being turned in the opposite direction. And that can end up essentially excavating soil up ahead of the wheel that you're being dragged through. And compared to the other situation where any of that soil motion is being moved to behind where your wheel is moving to. And so we looked at what the wheel torques are in these situations. We didn't have torque sensing, but we had power sensing, and we had encoders, so we could just divide power by angular velocity to estimate torque. And we saw that within this range of half the width to r prime, which 2/3 of r prime fell in that range, we saw this much higher torque in that range. The other thing we saw was that if you are actually at r prime, so your inner wheels are actually not rotating, and you're moving through loose soil, you're essentially dragging dead weight through the soil, bulldozing through. And not only that, but even if you're perpendicular to the direction that you're moving, having your wheels turning ends up reducing the resistance force than a wheel that isn't turning. That's what we see on this here. This is the force along the direction of motion. It's negative, it's a resistance force. When we turn the wheel, we still get resistance against that motion, but when we have a locked wheel that's not turning, we actually see much higher resistance there. So what this told us is that despite the model for hard ground telling us we want to have turning radii of r prime, when we apply that to driving in loose soil, which the model doesn't explicitly account for, we actually want to avoid these areas of operating just under and around r prime. And this sort of observation here was consistent with some observations we've made back when I was a student here, where we saw that there's a difference in the kind of soil motion that happens under a wheel if it's being driven or if it's being towed or dragged through the soil. So what we ended up doing was something similar to the experiments we did on hard ground, but now on loose soil, where we had, as a function of the turning radii, normalized by r prime. So at 1, this is a turn at r prime, and then 2 is slightly wider at twice r prime, 3 is at 3 times r prime, and so on. And again, we see energy savings as a percentage, so minus 20 representing 20% energy savings in this data here. And so essentially we, in and around r prime and just under it, we didn't see these savings in energy that we saw on hard ground because of the reasons that I just explained. But if you go for a slightly larger turning radii, you avoid those problems, and you can still get a savings in energy of up to about 20% for your maneuver, your CLC versus PLP. I had a PhD student who actually went through all the theoretical analysis to do optimal control for what are the optimal kinds of trajectories that you want to take with these kinds of rovers. And he came up with this beautiful piece of abstract art, which essentially represents the different types of trajectories that end up being optimal depending on your rover configuration. The way to interpret this is that you always are trying to end at the origin of this plot. And depending on where you start relative to this origin, so let's say you start in this blue area here, then we color code that with this royal blue. That means the optimal path is a CLC, so a curved straight line curve. That's what is the optimal path to get here from here. If, on the other hand, you're in this sort of orange place, that corresponds to a CLCC. So what you need is a curved arc, straight line, and then a curved arc and another curved arc. There's a whole bunch of math behind how this works. But the main conclusion that we could draw from this is that in and around, if you're only doing small maneuvers, then you might have to do some complex motions that are essentially like parallel parking type maneuvers. But once you get further than a rover width away between your start and goal locations, then you really have just 3 types of maneuvers that end up being optimal. Your CLC, CLCC, or CCLC. And so we went and did similar tests for some of those configurations where we needed to add an additional curved arc to our CLC path, and also showed that we could get energy savings relative to point turns, straight line point turns when we were in those conditions. So that led us to develop a series of recommendations on what turning radii to use depending on the condition you're in. And essentially, if you're on hard ground, say on Martian bedrock or something like that, then driving with at R prime turns is your best bet. And if you can't because of obstacles in the way or something like that, then operating as close to that as possible gets you as close to the optimal energy use. On soft soil, on the other hand, like Martian sand or lunar regolith, you definitely want to avoid turning at these sort of turning radii. But you can still get energy savings if you operate your turns at about 3 times your R prime. And if you don't have enough room to do those kinds of turns, well then point turns are your next best bet. And this can be used in many sort of practical ways. If you have sort of global waypoints that you're connecting, just round the curves between them at your sort of optimal turning radius that you've identified. Sometimes there are some situations where doing these more complex, like a CCLC curve, is practical and optimal. Like you need to back away from your crater anyway, so you might as well be turning while you back away and then sort of do your CLC around the bend. And if you're traveling along a straight line and come across an obstacle, then creating a new waypoint and having these CLC curves between your local points are a useful way to operate in these. Of course, energy efficiency is just one of many considerations for your path planning, but at a sort of low level for these local paths, having these turns at optimal turning radii can result in lower energy consumption, which means longer mission duration, more energy when you get to your scientific target of interest to operate your sensors and so on. So with that, just wanted to sum up some of the key takeaways. One being that operating in reduced gravity can significantly reduce your traction, so be sure to keep that in mind. Granular scaling laws seem to be the most promising approach on Earth for accounting for this from the experiments we've run at least. And the nice thing from that is that if you're operating at low enough speed, then and in mildly cohesive simulants, then it can actually be quite convenient to operate with that because you don't actually need to change your rover much. Then on the field testing side of things, paths that involve curved arcs can save you energy, and there are various sort of path choices like CLCs in most cases that can be your most optimal approach depending on your scenario. But most importantly, don't forget what I learned when I was here, which is to never stop getting out into environments that are as close as possible along all the different dimensions you can think of to where you actually want to eventually operate. Thanks very much.
More questions. So on the scaling laws, you spoke about the fluid number. Do you have kind of a high level recommendation? What is that speed, say at low speed? Is it 10 centimeters per second? Is it 2? I think it was more like 2 when you were talking about that.
So it depends. It depends on the size of the wheel. That's part of what comes into the Froude number. That's your L in the Froude number. Oh, that's not updating. Sorry. I can't just go directly to the slide. Okay, so because L comes in here, it depends on that. So from my review of literature, I haven't done my own investigation on this. I found these plots that weren't directly looking at this, but were just saying, hey, the velocity doesn't have an effect within these ranges. And then I went and computed what these Froude numbers correspond to from these tests, and they were all less than 0.05. So I would use that as a good starting point in terms of guidelines for what seems to be a reasonable Froude number to stay under. And the only implication here, if you're above that, it just means that you need to do this velocity scaling in addition to it. It's just, if you happen to be below it, then you get the added benefit of not even having to do velocity scaling.
In this slide, what does P represent?
Yeah, sorry, I didn't want to go through all of this, but I have it, it's better here. P is power, so, the batteries are low. But this is arranged in terms of inputs and outputs of your test, the outputs on the left-hand side, and the top number is the main quantity you're after. So this is drawbar pull or net traction, Z is your sinkage, and P is your power. And so those are the output metrics we looked at, but each of those needs to be scaled also accordingly by the granular scaling laws. And things like drawbar pull FD over mg, for those of you who've looked at drawbar pull, that's the drawbar pull coefficient. That's a commonly used non-dimensional traction number.
Back on that Froude number, the underlying continuum equations that govern this are the flowic equations. And yes, they were originally written in the realm of fluids. So there, if you think of one of these wheels, they even look like the paddle wheel on an old paddle wheel boat. And there's a big difference between going slowly enough that you're not whipping up a rooster tail and really paddling up for high traction and throwing a lot of inertia. And then for anyone who has paddled, I don't know if anybody in here has ever been in crew. Those are very long oars, and when they're a canoe, a lot of people paddle a canoe. So when you're going along and paddling, it's drag. You're slow enough that it's drag that's moving you along. If you're coming off the start of an Olympic C1 canoe race, at those first strokes are highly accelerative, and they produce amazingly high forces. The reason I started with crew is that back in the day, with big, huge legs and really being a beast, a great oarsman off the kickoff line can actually break one of those oars, and they're built. Anyway, it always struck me, like, why the heck is inertia in these equations ever anyway? We all look at that thing and it's kind of inching along like nothing. And the other, you look at it and it's steady state. So what the heck is going on? And Chris nailed it and described very well. It's actually to move those grains, they've got to go from nothing to something and back. And F equals ma, and if you want to move, you want to get them going, it's inertia. The good news, the saving grace for the CMU brand of this for now is we're slow. But there's a lot of headache and heartache in this for us also. The mobility that we overconfidently projected and counted on isn't there. So it was interesting also, to illustrate the difference between these phenomena, the power phenomena on solid medium versus granular. And I think that one actually helps CLU for the heartbreaking issue that we have no suspension. So that means that when we are driving on hard surface, we are a two-wheeled rover that, sure, it'll tip to the third one way or the other, but there's no force under it, there's no traction under it, it doesn't pull. And to some extent, not yet evaluated, because the key wheels that are touching have double the force. The one that's in the soft medium sinks somewhat. And that puts one of the other, the grousers from one of the other, or both of the others, down in the dirt also, so that they're pulling. Yeah.
One more question, Chris, is that okay?
Sure.
We still, we're over time.
No, go ahead.
I don't want to hold it. Yeah, on your skid steering optimization work, how much do you think the severing pattern, I guess, the tread on the wheels have an effect on what you observe? In other words, if you had like a perfectly smooth wheel and it was unpowered versus powered, would you see those savings even when you go sideways?
So it does have an effect. I still believe that you would get the savings. To answer your question directly, I think you'd still get the savings, even if your power consumption during point turn versus a wider arc is the same. If you're making progress with a wider arc turn and shortening your L, you still end up saving energy from the integral. So that's one thing. But we've looked at some effects of tread patterns and wheel shapes specifically for point turns. This was also working with the JPL Cadre wheels, which have these thin wheels. And we found that for skid steering specifically, one nice type of grouser pattern is slanted grousers, meaning they come across the wheel not perfectly perpendicular, but at an angle roughly equivalent to the angle that the wheel will be to your circle as you point turn through. So tread pattern and grouser pattern does matter. And a lot of times I was showing you want to do wide arcs when you can. A lot of times you need to do point turns operationally anyway, right? And I mean, you have a skid steer rover, you're going to want to do point turns. And yeah, your grouser pattern can help for that, for sure.
Yeah, actually, some of the work that Scott Moreland of JPL and we've done together was looking at those angled grousers front and back for better point turning. Can you jump to your abstract art slide? I think it was 29, but now your number is just so I can understand this better. the third term there, your pi over 4, that's an orientation. Is that right?
Yeah. So this is
This is for
this is
everything, is it one orientation?
yeah. This is a slice through, like, this would be a stack for each starting angle relative to the, your endpoint is 0, 0, 0, x, y, theta. Your starting point is x and y as shown on the plot, and pi over 4 because it's a slice.
Okay.
So, and that's why, sorry, I glossed over that. But
always end at the same orientation.
but you're always ending at the same orientation. So any start to end configuration will be encoded within this stack of, if your thetas. And this thing basically slightly rotates and contracts as you move through that stack. But the general form of it stays consistent.
And if you want an arbitrary starting orientation, an arbitrary ending orientation, you add another dimension to all that.
So, I mean, you can always, this is just saying that you're placing the origin of your coordinates at the end point. So, you mean, sorry, if you're unconstrained, like you don't care what orientation you end up as long as you're at the right point. Yeah, so that's an interesting question for this. We didn't look at that directly, but essentially that gives you freedom from within the stack to be where, it would actually, surprisingly, it would make the problem a little harder in that it gives you more freedom, degrees of freedom, in terms of where to search on this. Here, it's like if you know the exact starting and end poses, then you know exactly where in the stack and where on the plot you fall, and you just need to do the computation once. You could just arbitrarily pick and then do that, or you could do a broader search if you have the freedom of choice of your start and end thing. But you'd have to search through the various portions of the stack that are consistent there. That's an interesting question.
What's the optimal path? Does the velocity of the rover affect what the optimal path is, or are they independent?
So that's a great question. This theoretical work is based off of models that exist, so models for hard ground. For hard ground, the velocity, it turns out, doesn't matter because the frictional assumption means that if you're going twice as fast, the only difference is that it takes you half the time, so your integral works out to the same. Now, how that translates to the working on the granular terrains, we haven't looked into that. We've seen significant differences between model and reality on the parts that we have looked at. So I would be cautious about that. But again, if we're operating in the domain of relatively slow velocities and so on, I would imagine that it won't make a difference. But in the general case, this doesn't take into account granular terrains and the possible effects of velocity, sort of like your turning radius then can be velocity dependent, right? Not just input dependent on the relative differential velocities. So there's no super easy answer to that question, but But yeah, it's a good one.
Yeah, I just thought that the inertial example for both of them wasn't quite complete in anything I said. The big difference between accelerating and drag, of course, people know one's velocity, one's inertia. But when you pull that paddle, the inertia of the paddle is not. It carries with it this equivalent, this mathematically equivalent mass called added mass, which is a huge bubble of water. And gallons of water are a lot of mass. And when you pull against that, the reaction and the counterforce is huge. And it's the same thing here when you are moving, even in steady state, because of moving all the particles. There is an equivalent volume of granular medium, which is a lot of mass. It's very dense. And you don't have to accelerate it a lot to get significant forces.
And it's interesting to consider all of that in this context where we see that there's a difference in the amount of soil being mobilized depending on the gravity. Yeah.
And that's my premise with this idea that the big grousers are going to be down there grabbing and moving a greater equivalent volume, hence a much greater mass and a greater resistance.
So your results on the skid steer rovers on the power consumption, like they depend on the different kinds of soils, but do you recommend anything based on different gravities as well? Like, are they dependent on that?
So we haven't had a chance to look at that specifically. So my thoughts on that, just sort of from the intuition drawn from the other aspects of our work, are essentially what I said earlier, that at lower velocities, I think the results that we found here with sort of relevant masses and relevant size rovers and whatnot would actually translate pretty well in the lower gravity as well.
But did you ask about wheels?
Yeah, I was asking about the wheels, skid steer rover.
But whether was your question sorry, just to make sure I understood it, was your question whether the effective gravity would potentially change the recommendations about how to operate the skid steer rover?
Yep.
So yeah, so for that, I think our despite not having investigated it directly, I would say I'm confident that the results that we found in our field testing would still hold up.
I asked that because you recommend the same thing for like Martian soil and like lunar soil.
Yeah. So again, this is still assuming the paradigm of relatively slow rovers, so low Froude number rovers. But within that, I would make the same recommendations regardless of gravity level.
All right, thanks very much, Chris.
All right, thank you.